All right, howdy folks. In this video, we're going to go over this mechanism, which I would put in the electrophilic aromatic substitutions chapter. And this mechanism, I think, is one that hopefully students of all levels should be able to work towards solving. And as with most of our other videos, what I'll encourage you to do is actually to take a pause at this stage, try to work through this problem all on your own, see how far you can get, and then come back and watch the rest of the video after you've already approached the problem. As a reminder, for those of you that would like access to the PDF files of these questions, both before and after I've solved them, please go ahead and subscribe to us as a Patreon follower, and you can download all those PDFs in our Patreon account. All right, go ahead and pause right now. All right, welcome back, folks. What I'm going to do is walk through this mechanism, and a number of the things I've been trying to illustrate in these videos is always to try to look at what sorts of bonds are being made or broken when you compare the starting material and the product. And since this is part of the electrophilic aromatic substitution chapter, it should not be too surprising that we're going to end up with an electrophilic aromatic substitution, and specifically we're going to make the bond I've just dashed through. And we can kind of get there by mapping these two CH2s, and then we have that dangling OCH3. And what you'll notice here is we have 1 and 2 CH3s in the starting material, but we only have 1 in the product. And so that means at some point we're going to need to kick one of those groups out. The next thing I always try to do is to think about what kind of reagent I have. And up top here, you know, we have boron trifluoride diethyl etherate as our reagent. And that's a really great reagent to be a Lewis acid. And so that's what our note or our hint is here. Now, often I encounter students that are really kind of fundamentally confused by Lewis acids, and they can work through a lot of mechanisms just okay if we have H plus around. But as soon as we start introducing more complex Lewis acids, it becomes much more difficult. And the reason, by the way, that that's true is because you have more formal charges to keep track of on the Lewis acid. And so if you're experiencing that, please don't be frustrated by it. What I would encourage you to do is recognize that your formal charges are really what you want to focus on. The other thing that I'll say that's confusing about Lewis acids is that we have a lot of them. So within the organic synthesis community, we probably have thousands, and even within the organic textbook, there's quite a few. So aluminum trichloride is a very common Lewis acid, iron trichloride, iron tribromide, BF3 etherate. There's a whole slew of Lewis acids, and because there's a wide variety of them, they can become confusing. What I encourage students to do that find themselves being a little thrown off by Lewis acid is I encourage them to think about the Lewis acids as H+. Both a Lewis acid and a Bronsted acid are both acids, and so they're both going to protonate things. And so fundamentally, they have the same innate or inherent reactivity. And so because of that, you can just imagine going through the whole mechanism with H+, and then substitute H+ for your Lewis acid later. And more often than not, that'll be just fine. So I'm going to do that up top here, and then I'll run through the whole mechanism again with the BF3 as we should do. So as H+, the first thing you're going to do is protonate something. And this is good because for those of you that have been following our electrophilic aromatic substitution videos, the other one can be seen here, is that we really want to try two kind of fundamental steps. So we want to make a strong electrophile. And so that's step one, is we're going to take some mixture of reagents and make something that's very electrophilic. And then the second step here is do EAS. And this is, remember, attack is step I, and then step II here is loss of H+. And the bottom half of this, step 2, the do EAS, is the same regardless of what the electrophile is and regardless of what the substrate is. So really all of these complicated, challenging mechanism problems come down to, can you make a strong electrophile? And protonating something is a really good way to do that, or binding it to a Lewis acid. Now our basic atoms are going to be the oxygen atoms. So they're the ones with the lone pairs on them. And so I'm going to start by protonating that intermediate. After you protonate an alcohol, it becomes a leaving group. After you protonate an ether, it can become a leaving group. And so that's what we're going to do here is we're going to kick off this protonated species, and that'll then we'll lose methanol out of here. So that's okay. And then I'll draw the rest of what that carbocationic intermediate would be. And this particular carbocationic intermediate is a special one. For those of you that have already gone through the chapter on aldehydes, you might recognize that this starting material is a special starting material because the central carbon here is bound to not one, but two different oxygens. And so it's technically an acetal. It's an acetal functional group. And acetals typically react through the resonance structure that I'm going to draw here. And this is what we call an oxocarbenium ion. It turns out it's a really great electrophile. And for those of you that are interested in learning more about oxocarbenium ions, what I would encourage you to do is go to the index of your book, look up acetal formation, and go look at that section, because that's typically where oxocarbenium ions are really kind of first introduced. All right, but for the purposes of our EAS mechanism, what we're going to do is draw an analogy to a Friedel-Crafts reaction. And so I'm going to delete my arrow here for this resonance structure, and I'm going to start back at this intermediate in the middle here, because this is the one now that's set for our EAS. And so we can take this set of pi bonds or pi electrons, and we can attack that carbocationic position. Ooh, and let me go ahead and label this. This is going to be our E+, so strong electrophile. And if we know we're there, then that means we've completed the first half of the EAS mechanism. So right there. So everything else now is going to be just following the standard two-step EAS mechanism. So this is going to be our initial attack. Oops, got one too many bonds in there. And so we should make this carbocation from using the double bond that I indicated. Of course, this has a number of resonance structures, and so we can put it in the most stable resonance form by putting that charge on the tertiary carbon. Like so. Like so. And overall, that's going to be A-OK. And now all we have to do is complete the EAS mechanism by loss of H+. And so that'll get us back to where we started with. And we're done. So that's the mechanism of this particular EAS mechanism. And of course, for this mechanism, what I've done is I've substituted that H plus or the BF3 etherate for H plus just to make it a little bit simpler. And because of that, then we can draw an analogy to our classic two steps here in every EAS mechanism. All right, what I'll do now is I'll transition and we'll actually draw out the full mechanism with the BF3 etherate. And for those of you that want a little quick refresher, remember BF3 ethorate's a Lewis acid because the boron is trivalent and it's got 3 ligands and it's got an open p orbital then that we can attack with a pair of electrons. And so that's the nature by which BF3 becomes strongly Lewis acidic. And so we can have this attack boron, and so that will then generate our adduct, our Lewis base, Lewis acid adduct. All right, and so here's one of the things that makes it more confusing. Way back at the beginning, I mentioned formal charges, and because we have a positive oxygen atom now, and we started from 2 neutral things, that means something needs to be minus. And the thing that should be formally minus then is the boron, because now it has 4 ligands. And so if you go through and do the full formal charge analysis, you'll figure out that the Lewis acid ends up with a formal minus charge. One thing I like to point out is remember that that is the formal charge. It doesn't really represent where that charge exists on a molecule kind of in real life, if you will. Those fluorine atoms are very electronegative, and so they're going to pull that density towards them and away from boron. And so realistically, that negative charge is distributed across the 3 fluorine ligands on boron. In any event, what I'm going to do now is invoke a little bit more complex resonance, and I'm going to kick off that leaving group. And when I do that, I'm going to make my oxocarbenium ion directly. And now what we can do is engage that oxocarbenium ion with our nucleophilic arene and start the EAS mechanism. Oops. And instead of drawing all the resonance here, what I'm going to do is just so there we go. We have our product, and most of the time, H plus is not just going to fall off in the vacuum. It's going to be pulled off by something. And so we can go ahead and finish balancing out this full equation right now. And because this overall is minus, we're probably going to have that OME attack there. And what that'll give us then is our BF3 back plus methanol. And so all in all, we're going to end up with the exact same products that we identified up top here, where we had methanol come out nice and early. And so again, 2 different arrow pushing representations here, one with H+, but if you go through and compare the steps, you can see that it's basically the exact same mechanism with H+ as it is with the Lewis acid. And so again, if you're thrown off by using a Lewis acid instead of a Bronsted acid, I would encourage you just to think about it as a fancy Bronsted acid until you get comfortable with the formal charges and recognizing where that Lewis acid goes. All right, thank you for listening to this one. What I'll do is remind you that if you're finding these videos helpful and if you're getting some use out of them, please tell a friend. Please subscribe to our YouTube channel. The number of YouTube followers in the comments lets us know how good of a job we're doing, and it really provides some encouragement to keep trying to make these videos. If you want access to the PDFs, remember you can go ahead and follow us on the Patreon page, and hopefully you could also give us a like or a retweet on Facebook or Twitter. So with that, thank you. Please go ahead and watch the next video or leave a comment below.